Today, we are going to journey tens of thousands of kilometers into space, explore the hidden physics of planetary magnetic fields, uncover the history of how we discovered this invisible shield, and travel across the solar system to see how other worlds fare with or without their own magnetic defenses. This is the story of the Magnetosphere, the invisible guardian that defends every planet lucky enough to have one. To understand the magnetosphere, we first must understand the threat it faces every single second of every single day. Our sun is not a gentle, steady ball of light. It is a roiling hyperactive star that constantly spews out a stream of charged particles, electrons, and protons, called the solar wind. This stream races outward at hundreds of kilometers per second, sweeping through the solar system and slamming into every planet, moon, and object in its path. On top of the steady solar wind, the sun also unleashes massive, violent eruptions known as coronal mass ejections, or CMEs, billions of tons of magnetized plasma that explode outward at speeds up to 3,000 kilometers per second. If these particles and storms were to hit a planet directly, they would slowly erode its atmosphere, break apart molecules essential for life, and flood the surface with radiation that damages DNA and destroys complex organisms. For decades, scientists wondered how Earth survived this constant cosmic assault, and the answer lay hidden in a force we experience every day but never truly see: Earth's magnetic field. Deep beneath our feet, nearly 3,000 kilometers below the surface, Earth's outer core is a churning ocean of molten iron and nickel. This liquid metal is extremely hot, electrically conductive, and constantly in motion due to Earth's rotation and heat escaping from the inner core. This movement creates a natural dynamo effect, generating a powerful global magnetic field that extends far out into space. This magnetic field is not just a small local phenomenon. It stretches outward to form an enormous comet-shaped bubble known as the magnetosphere. On the day side, the side facing the sun, the solar wind compresses the magnetosphere to about 6 to 10 times Earth radius, roughly 60,000 to 100,000 kilometers above our surface. On the night side, facing away from the sun, the solar wind stretches the magnetic field into an immense flowing structure called the magnetotail, which can extend hundreds of Earth radii into space far beyond the orbit of the moon. This entire structure is our planet's invisible shield, and it works in ways that are both elegant and powerful. The discovery of the magnetosphere is one of the great triumphs of the early space age, a story tied to the first steps humanity took into orbit. Before the 1950s, scientists suspected Earth had a magnetic field, but they had no idea it created a vast protective bubble in space, or that it trapped high-energy particles around our planet. All of that changed in 1958, during the International Geophysical Year, a global effort to study Earth and space. On January the 31st, 1958, the United States launched Explorer 1, its first successful satellite, built by a team led by Wernher von Braun, with a critical instrument designed by physicist James Van Allen. Van Allen's Geiger-Vler counter was meant to measure cosmic rays in space, but it returned shocking, unexpected data at certain altitudes. The detector was flooded with so much radiation that it went off the scale. At first, scientists thought the instrument was broken, but follow-up missions, Explorer 3 and Explorer 4, confirmed the same pattern. Van Allen and his team had discovered two huge donut-shaped belts of trapped high-energy particles encircling Earth, now named the Van Allen belts in his honor. This discovery was the first direct proof that Earth's magnetic field creates a protective structure in space, the magnetosphere. Overnight, our understanding of our place in the solar system changed forever. We realized we lived inside a cosmic safe, shielded from the harsh realities of interplanetary space. Let's break down how this shield actually works, step by step, so you can visualize this invisible process. When the solar wind hits the magnetosphere, the first thing it encounters is a boundary called the bow shock. Think of this like the bow wave of a ship moving through water. It slows down, heats, and deflects the incoming solar wind before it can reach the main protective layer. Just behind the bow shock is the magnetosheath, a turbulent transition zone where the solar wind particles swirl and slow further. The next critical boundary is the magnetopause, the exact line where the pressure of Earth's magnetic field balances the pressure of the solar wind. This is the true outer edge of our shield. Beyond it, the solar wind dominates. Inside it, Earth's magnetic field rules. Most charged particles from the sun are deflected around the magnetosphere, flowing past our planet like water around a rock in a stream. Some particles, however, are trapped by the magnetic field lines and pulled into the Van Allen belts, where they bounce back and forth between the north and south poles, unable to reach the lower atmosphere or surface. This trapping mechanism is life-saving. It locks dangerous radiation far above our heads, where it cannot harm living things or damage our technology. But the magnetosphere is not a rigid, unchanging wall. It is a dynamic living system that responds to every shift in solar activity. When solar storms grow stronger, the magnetosphere compresses and twists. When the sun is calmer, it expands and relaxes. One of the most beautiful side effects of this interaction is the auroras, the northern and southern lights. Occasionally, some charged particles slip through the magnetosphere's cusps, funnel-shaped openings near the magnetic poles. These particles race down along the magnetic field lines and collide with oxygen and nitrogen molecules in Earth's upper atmosphere. These collisions excite the gas molecules, causing them to glow in brilliant shades of green, pink, red, and purple. What we see as a stunning natural light show is actually the magnetosphere at work, safely discharging energy from the solar wind before it can reach the surface. Every aurora is a visible sign that our invisible shield is doing its job, protecting us with elegance and power. To truly appreciate Earth's magnetosphere, we must look at our planetary neighbors and see what happens when a world lacks this critical shield. Let us start with Mars, the planet most like Earth in many ways. Billions of years ago, Mars likely had a thick atmosphere, liquid water on its surface, and even a global magnetic field just like Earth. But over time, Mars' small core cooled and solidified, shutting down the dynamo effect that generates a magnetic field. Without a global magnetosphere to protect it, Mars' atmosphere was slowly but steadily stripped away by the solar wind. Today, Mars has only a thin, wispy atmosphere, no liquid water on its surface, and constant high levels of radiation. It is a cold, dry, dead world, a stark warning of what Earth would become without our magnetic shield. Venus, our other neighboring planet, tells a similar story. Venus has no intrinsic magnetic field, no dynamo in its core, and thus no true magnetosphere. Instead, it has a weak induced magnetosphere, created by the solar wind, interacting with its extremely thick atmosphere. While this induced field offers minimal protection, it cannot stop the solar wind from slowly eroding the upper atmosphere, and Venus' brutal surface conditions, hot enough to melt lead, show that a thick atmosphere alone is not enough to make a world habitable without a magnetic shield. Not all planets have weak or missing magnetospheres. The gas and ice giants of the outer solar system have some of the most powerful magnetic shields in the entire solar system. Jupiter, the largest planet, has a magnetic field nearly 20,000 times stronger than Earth's. Its magnetosphere is the largest single structure in the solar system, so big that if it were visible from Earth, it would appear larger than the full moon. It stretches more than 21 million kilometers wide, 150 times wider than Jupiter itself, and its magnetotail extends all the way to Saturn's orbit. Jupiter's magnetosphere is so powerful that it traps enormous radiation belts and creates intense auroras, far brighter and more energetic than Earth's. Saturn too has a strong magnetosphere, shaped by its famous rings and its moon Enceladus, which spews water vapor into space that becomes ionized and feeds Saturn's magnetic system. Uranus and Neptune have strange tilted magnetic fields offset from their rotational axes, creating weird, lopsided magnetospheres that shift and change as the planets spin. Even tiny Mercury, the closest planet to the Sun, has a small, weak magnetosphere, enough to deflect some solar wind, but not enough to hold onto an atmosphere. These examples teach us a universal rule. A strong, stable magnetosphere is closely tied to a planet's internal structure, its core activity, and its ability to hold onto an atmosphere and support life. NASA has spent decades studying the magnetosphere to unlock its secrets, using a fleet of dedicated missions that have revolutionized our understanding. After the Explorer missions discovered the Van Allen belts, NASA launched the Van Allen probes, two spacecraft that operated from 2012 to 2019 to study the belts in unprecedented detail. These probes revealed that the belts are far more dynamic than we thought, swelling and shrinking in hours in response to solar storms, and even forming temporary third belts during extreme space weather. Another groundbreaking mission is NASA's Magnetospheric Multi-Scale Mission, or MMS, 4 identical spacecraft flying in tight formation to study magnetic reconnection, the process where magnetic field lines break and reconnect, releasing massive amounts of energy. Magnetic reconnection drives auroras, solar storms, and radiation belt dynamics, and MMS gave us the first direct observations of this fundamental physical process in space. These missions do more than satisfy curiosity. They help us predict space weather, protect satellites, GPS systems, power grids, and even astronauts traveling to the Moon and Mars. Understanding the magnetosphere is not just about space science, it is about protecting our technology and our future in space. The importance of the magnetosphere goes far beyond our solar system. It is a key factor in the search for habitable exoplanets across the galaxy. Astronomers now list a magnetosphere as one of the top requirements for a planet to support complex life. A rocky planet in the habitable zone might have liquid water and a thick atmosphere, but without a magnetosphere, solar wind and cosmic radiation will strip away its air and make the surface unlivable. As we discover thousands of exoplanets, we are starting to look for signs of magnetic fields using aurora's radio emissions and stellar wind interactions to identify which worlds might have the invisible shields needed to protect life. The magnetosphere, once a little-known detail of planetary science, has become a cornerstone of astrobiology, helping us answer one of humanity's biggest questions: are we alone in the universe? When you look up at the night sky, you are not just looking at stars and planets. You are looking at a cosmos full of worlds, each with its own story of survival. Some have strong protective magnetospheres that nurture life and stability. Others lost their shields long ago and became barren wastelands. Earth is one of the lucky ones, a planet with a churning molten core, a powerful dynamo, a vast magnetic shield, and all the conditions needed for life to thrive. We often take for granted the air we breathe, the water we drink, and the safe world we call home, but none of it would be possible without that invisible bubble of magnetism floating above us. The magnetosphere is not just a scientific curiosity. It is the quiet hero that makes every moment of our lives possible. We have journeyed from the depths of Earth's core to the edges of the solar system, uncovered the secrets of the invisible shield, and seen why it is the most important line of defense for any habitable planet. We have learned how it forms, how it protects us, how we discovered it, and how it shapes the fate of every world. The next time you see an aurora, or simply step outside and feel the calm of a quiet day, remember the invisible force working tirelessly above you, the magnetosphere, our cosmic guardian, the invisible shield that defends our planet. Please like, comment, share, and subscribe to the channel.